Okay, we can show an equivalence between context-free languages and non-deterministic push-down automata by creating an algorithm that takes a CFG and turns it into an NPDA. And this is the direction that's useful for practical problems, because given some CFL, we want to actually create the automata that recognizes strings from the language of that grammar, which is useful for parsing things for compilers and input for programs and that sort of thing. So how do we do it? So given a CFG, we create an NPDA. The NPDA has got three states: in the initial state, the working state, where the working state is the only state that really does everything, and the final state, Q2. We declare the alphabet to be the set of all terminal symbols of the grammar, and we declare the set of all stack symbols to be terminals and non-terminals, and we include the special character Z. That's the initial stack state symbol. All right. So the first thing we do is we initialize. So in the initial state, I read no input. I see an empty stack. I transition to Q1 and push S onto the stack, where S is the starting symbol for the grammar. What I do from there is I can expand all non-terminals. So for every production rule of the form X goes to beta, where X is a non-terminal and beta is some string of garbage, what we can do is from the working state, deliberately read no input, see an X on the stack, pop the X off the stack, and then push what X transitions to on the stack. So pop X, push beta, if there's a transition from X to beta. We then match and pop terminals. So for every terminal symbol, if I see a terminal on the input and a terminal on the stack, I read the X from the input, I pop the X off the stack, and then push the X back on the stack again. That doesn't feel right. That should be an epsilon. Yep. Pop the X. I read the X off the input, pop the X off the stack, and then consume them both. So that should be an epsilon. And then you terminate when your input is all blanked out and your stack is empty, so everything's all balanced out. And then you transition to Q2. Okay? So let's just try cracking this algorithm out for this example here. So stage 1 is always exactly the same. You initialize. Q0 epsilon Z goes to Q1 SZ. Stage 2 is to expand all non-terminals. So if I'm in state 1, I ignore the input. If I see an S, I consume the S and push TU. Okay, and we keep cranking them out. So if I see a T, I'm going to pop the T and push ATB. I could also, if I wanted to, seeing a T, decide to push epsilon instead, right? Because this grammar can pick one of these two options. So this NPDA is going to have it's going to be an NPDA. It's going to be non-determinism, because here I can choose which path to take. Okay, we continue. So Q1 epsilon U goes to Q1 AU. It could also go to V instead. Q1 pop U push V. Okay, we keep going. So we now do the cases for V. So Q1 epsilon V transitions to Q1 CV. Delta Q1 epsilon V can also transition to Q1 epsilon. Okay, so that's expanding everything. Rule 3 is to match and pop terminals. What are my terminals? A and B and C. So if I see an A on the input and an A on the stack, I read the A and I pop the A off the stack, so I delete them both. And the same for B, Q1 epsilon, and the same for C. Q1 epsilon. Okay, so that's the terminals dealt with. And the last case is if the input is empty and the stack is empty, everything's balanced out, then I accept. So given empty input, given I can see the empty stack symbol, I transition to Q2 and then hold. Okay, so that's how you convert a CFL into an NPDA. Let's do a trace of this. So what's a string in this language? S goes to T, T goes to A, B, T, and then to epsilon. So it looks like A, B, and then we'll throw in some A's from U, and then a C from V. There we go. That looks like it's going to be a string on this language. Why? I can create a pass tree for it. So S goes to TU, T goes to ATB, T goes to epsilon, so that's the A and the B dealt with. And then U can produce two A's, and then go to V, produce a C, and then go to epsilon. A, epsilon, B, A, C, epsilon. There we go. So given the grammar can produce it, it should be the case that the NPDA can accept it. So we can produce a trace, which is basically like the state of the machine, like you just a full machine like log printout, if you like, a list of the state of its visits as it goes. So we start in the initial state. We start with our input being A, B, A, C, and we start with the initial stack symbol. Okay? This rule here tells me pop the Z and push S and Z. So this is going to be transition to state 1 from Q0 to Q1. Read no input, so the input stays the same. And then push SZ. Okay? What's next? If I'm in Q1 and I see an A on the input and an A on the stack, I can pop them off. Well, that's not the case. I can't use that rule. What rule can I use? It looks like it's going to have to be the rule with an S. There's only one rule for that. Pop S, push TU. So we'll do that. A, B, A, C, C. Pop the S, push TU. So you have TU, Z on the stack. Okay. Now what rules can I apply? Look at the only rules I can apply are going to be rules with T's in them. And I want to match the A's. That means I'm probably going to have to push an A on the stack. So it looks like I'm going to want to use this rule here. Again, I have to make a deliberate choice, right? Much like I made a deliberate choice to not choose the wrong path down this pass tree, I have to be careful to make the right choice here or I might get stuck. So as long as this trace has some path to victory, if and only if there is some pass tree that produces a string. So you might get stuck, right? If you want to prove the string's rejected, you have to branch out and show that every possible path to victory will fail. Much like for accepting strings for an NFA. So let's continue. So I'm going to replace the T with ATB. A, B, A, C, C. T goes to ATB. And now I can pop both using this rule here. So read an A from the input and read an A off the stack. Okay. I only use the ATB transition once from the pass tree, so it looks like I should now send T to epsilon. B, U, Z, that should be an uppercase U. And now I can match the B's using this rule here. So you can see how the trace is going to very similarly follow the pass tree. It looks like I'm going to have to use the AU transition twice, as we'll see. So I'll replace U with AU. Whoops, what happened now? I transposed one of my A's to a C. Whoopsies. A. That's better. So pop U and push AU. Go back to the same state. Okay, and you can only ever see the top of the stack. So all the PDA can see is that A on the top. So I've got to pop and match the A's. We're going to delete this A, delete that A. So we have A, C, U, Z. Push the A back on using this rule here. A, C, A, U, Z. Pop the A's. C, U, Z. Send U to the V transition. So pop U, push V. And then I have to add a C using the V transition, which is this rule here. C of V, push a CV. Read no input. Pop and match. And now I can get rid of the V. So V goes to epsilon. So pop the V, push, nothing by this rule here. Okay, now I'm in a state where the input is empty and the stack is empty, so that means I can now transition to the final state. Read no input, pop the final stack symbol. And because we finish in Q2, we accept. Okay? If I wanted to check that a string failed, I would have to branch all possible options. So whenever I come to a point where I have to make a decision, I have to try both decisions and show that no matter what path I take, I always get stuck. So we'll try that next.